Good afternoon. My name is Eric Mucklow from the headquarters of the U.S. Army Corps of Engineers. I'm the Building Technology Standards and Criteria Program Manager. With me today is Jack McAllister. He's a mechanical engineer who works for the Corps' Hydroelectric Design Center. He has worked in that capacity for nearly 3 years, and his work has been related to both the rehabilitation of Corps-owned hydropower plants as well as inquiries and investigations related to small hydro. Today's webinar is on the latter, Microhydro. This Microhydro webinar is intended to provide course participants with some familiarity with the topic of small-scale hydropower. The course will introduce the basics of microhydro equipment, the fundamentals of assessing sites for microhydro potential, and an overview of the process for executing a microhydro installation project. Discussion will cover both technical and non-technical considerations involved in microhydro site feasibility analyses, as well as a brief overview of the economics involved in scoping a microhydro installation project. The webinar content largely reflects what is presented in the Microhydro Tech Note, that's Tech Note number 28, which is hosted on the Whole Building Design Guide, and will include a description of the small hydro feasibility analyses which the HDC has been involved. With that, I will now turn it over to Mr. Collister.
Thank you, Eric. Design Center, or HDC. I've worked in this position for a little over 3 years. What I'm presenting today addresses the topic of microhydropower, and I will be covering essentially the same scope as what is presented in the tech note that invitation webinar. Now, first I would like to provide a little background on HDC's role for those who are not familiar with our office. Per the official definition, HDC is the mandatory center of expertise, performing planning, engineering, and design, maintaining expertise, and developing standards for the U.S. Army Corps of Engineers, hydroelectric power facilities, and large pumping plants. In other words, if there is any significant refurbishment or rehabilitation work being done at Corps-owned and operated powerhouses, HDC gets involved in a technical advisory role. Within this niche role, HDC's technical involvement is focused on hydropower equipment. For the full execution of a contract, there are many other USAID professionals who are involved at, say, the district level. And that is to say, HDC is not a full-service organization. This is true for the larger powerhouses that we work with, and certainly extends as well to Microhydro. And as I will discuss a little later on in the presentation, a number of these different professionals at the district level or division level will need to be involved in a microhydro project as early as the scoping or the feasibility study phase. My goals in presenting this to you today reflect the goals of the Microhydro Tech Note. Namely, I hope to provide an introduction to discussing hydro and its related equipment, especially in regards to the microhydro range. After discussing hydro and hydro equipment, I will present the factors and considerations that form the basis of analyzing a site for its ability to support a microhydro installation. Ultimately, I hope to convey a sense of what is necessary to answer the question, do I have a site where microhydro... Before I start introducing equipment, I would like to give you a preview of the blueprint. I will revisit this a little later on in the presentation with some actual numbers and equations, but for now I would like to introduce it as a constant. Fluid power, expressed as an ideal, is a function of pressure and flow. By ideal, we are saying that the equation expresses the maximum amount of power present in a fluid stream. In an actual application, we will observe losses within the water passage and losses given the hydraulic efficiency of the turbine. If we are to consider the fluid power available in a given stream, we want to be sure that our initial assessments of head and flow are reasonably accurate. If we overestimate the available flow or head, we are potentially setting ourselves up to pursue a feasibility study further than it should be taken, or to create a situation in which we suddenly discover rather late in the process that our economic considerations, equipment sizing considerations, and method of application will all need to be adjusted. For some streams, also note that measuring the flow at a given point of time might only be providing a seasonal snapshot of that stream's characteristics. So it is important to look at historical data if the stream under consideration is subject to seasonal variation. Going in hand with the fluid power equation that I just introduced, I will mention a little more about these terms that hydro engineers tend to throw around. Engineers working in hydro or with pumps or other turbo machinery say flow to refer to volumetric flow rate, or the volume of fluid per unit time moving through a stream or a conduit or through turbo machinery equipment. In the hydro industry in the U.S., our most common unit for flow is cubic feet per. Hydro engineers in other parts of the world we use cubic meters per second or occasionally liters per second. We may also commonly encounter flow in terms of GPM, gallons per minute, for pumps and piping systems. Conveniently, flow in a river or stream in the U.S. is also typically reported in cubic feet per second. For instance, U.S. Geologic Survey gauges on rivers and streams report flow in CFS. Now, as we discussed with the ideal fluid power equation, fluid power is a function of flow and head. Head is the terminology we use to discuss the change in elevation in water. So in the U.S., typically we use units of feet, where the rest of the world might use meters. The true components of fluid power are actually flow and pressure, but we simplify the variables we're working with by treating the specific weight of the fluid, in this case water, as a constant, and then pressure is a product of multiplying specific weight by the head. So we treat that as the specific weight as a constant and then just deal simply with head, the change in elevation. Energy is the capacity to perform work. For a fluid stored in an elevation, the head, at pressure, is potential energy. Moving water has kinetic energy. Power is the rate at which energy is transferred. If we consider a relatively constant head, then the power delivered by a hydroturbine is controlled by controlling the flow. In other words, the rate of flow goes hand in hand with the rate of energy transfer to the turbine. When discussing small-scale hydro, you will hear a number of different prefixes applied in their application relative to the scale of a hydro unit, that it is consistent with the definitions as I've listed here. Small means less than 10 megawatts. Mini hydro is between 100 kilowatts and 1,000 kilowatts, or 1 megawatt. Microhydro is between 10 kilowatts and 100 kilowatts, and picohydro is less than 10 kilowatts. For comparative scale, the larger use-phase powerhouses that we work with may range from several dozen megawatts to an excess of 1,000 megawatts. For example, the installed capacity of Bonneville Dam on the Columbia River just east of Portland is a little over 1,000 megawatts. Now that's the full capacity of the installation of all the units in the two powerhouses there, and each individual turbine generator there is in the range of 54 to 66 megawatts. And for some scale as to at the other end of what 1 kilowatt or 1,000 watts might be, I recently purchased a blender that is a 1,000-watt blender. Now, as I start to discuss specific types of hydroturbines, I will divide them into two general classes. One of these classes is closed conduit. This indicates that there is a pressurized passageway or pipe, or what we would refer to as a penstock, that delivers the water to the turbine. As a closed conduit would typically be pressurized by the head, the closed conduit turbine is treated with the ideal power equation that we discussed. Its power is a function of both pressure and flow rate. On the other hand, an open channel type unit is primarily spinning with the velocity of the flow, for instance, and does not see the pressure that is available in a closed conduit arrangement. First, I will go through a number of examples of closed conduit hydroturbines. Some applications in the microhydro range for a closed conduit system could be a dam with an auxiliary discharge pipe. Typically, the outlets from a dam were designed to serve specific purposes. In the case of many small flood control dams, the outlet tunnel may not have been designed to be pressurized. However, there are instances wherein dams have been constructed with an extra outlet pipe that can be pressurized to the head of the dam, such as a source for a municipal water or irrigation system that in some cases may not have ever been utilized. Some gravity-fed pipelines or pipe systems may include a pressure-reducing valve, and in this case it would be a great opportunity to apply microhydro, as that pressure-reducing valve could be removed and replaced with a microhydro turbine that instead captures that energy instead of just being dissipated by the valve. If you're considering an open stream that has an elevation change, you might introduce a microhydro system to that stream, assuming you have the ability to reroute some of that stream's flow into a pipe to take advantage of the elevation change. I will move through some examples quickly to demonstrate the range of equipment. I have organized these in an increasing order of power, and I want you to pay attention to the increase in equipment requirements and complexity as the size of the unit is increased. This first example is a Microhydro scale turbine manufactured by Scott. In other words, this is putting out less than 10 kilowatts. What we don't see in this picture is here. We're up here. There's a small dam or weir that's causing this creek to pool. And some flow is redirected, and instead of flowing down the stream, it's being routed through the hose here. And this small Microhydro scale turbine is set up so the turbine runner is on the left side of the housing here, and then there's a generator on the right side of the housing. And that small 5 or 10 kilowatts of electrical power is fed out through the line here. This is another example of a Microhydro turbine, but instead of the turbine, what I'm showing is the operating envelope. In this case, the operating envelope showing various turbine generator units manufactured by a company called PowerSpout. Note that this shows both of our factors for determining fluid power, the flow and the head, in terms of meters and liters per second. Also notice that the scale of these axes are in logarithmic scale, so not linear. So by a combination of flow and the head, we have these diagonal lines that show our power output for PowerSpout various units, ranging from 100 watts to 12 kilowatts. So if you're looking around at manufacturers' websites, you might encounter these, and feel free to reach out to HCC for assistance in interpreting what you're seeing. This next slide shows the Toshiba Hydro E-Kids equipment. These units range from the Microhydro scale across the Microhydro hydro, or 5 kilowatts to in excess of 200 kilowatts. So it covers a broad range of applications for head or flow. This slide is also brought from the Toshiba Hydro E-Kids website, providing some conceptual methods of intake for turbines. This image in the upper right, for instance, could have been a situation where this pipe was pre-existing and featured a pressure-reducing valve. And a simple system such as the Toshiba Hydro E-Kids system could be installed in place of that pressure-reducing valve to tap into that potential energy that's there in that flowing water through that pipeline. Here we are increasing our output a little bit. We're up to 75 kilowatts. This happens to be a station service unit at a dam in Afghanistan. A station service unit is typically installed to provide power to the hydropower house itself to support the operation of the powerhouse and its larger hydro units. Note that there is a substantial amount of head, 250 feet, available to this unit. So achieving a 75 kilowatt output does not require too much flow. And for that reason, the penstock, this gray pipe, is relatively small in diameter. Just to familiarize you with the equipment you see here, the gray pipe that I just indicated to the lower right is the penstock delivering flow to the turbine. And there's a shut-off valve to isolate the turbine from maintenance. Then the turbine, the unit here to which the water is passing. The actual rotating part of the turbine we refer to as the turbine runner. The water is directed in, wrapped around in what we call the scroll case, moves through the wicket gates, and then into the turbine runner here, which discharges in this direction. Off to the right here, this black piece is the black housing, contains the generator, and there's a governor at the left here that is going to control the output of the generator by controlling the flow through the turbine. Here's a more modern example of a same size 75 kilowatt unit. Notice the increase in the scope of the amount of auxiliary components as we start to move into this output range. Also notice with this particular unit, the draft tube that is required as part of the unit's setup. And that entails that along with this powerhouse that they've had to construct, the installation of the unit may have also required some extensive excavation work to allow for this style of unit to be installed. Now, to avoid that extensive amount of site work, there are other types of turbine units available. This example here is a cross-flow style unit. These are ones that I would particularly recommend exploring if looking into microhydro installation, as they are functional at rather low head ranges across a broad range of flow with a very large range. These values that I show here are the full range to which you might apply a cross-flow turbine, but not the actual output of a single unit. But for a single unit, a cross-flow unit would maintain a reasonable efficiency across a broad range of flow. And although lower than more common types of turbines, these are a good option based on that broad range or efficiency. And just to familiarize you with the equipment you see in the picture here, again, the depiction on the left is just reversed from what you see on the right. This actual installation on the right, I'm not sure the actual size, but would guess that it's within the microhydro range. And so it's fed by a penstock. And this arm here is part of the mechanism to open or close the guide vanes, which controls the flow through the turbine. There's the generator unit at the left, and then the governor and control mechanism in front there. So these next couple examples are units where we have crossed that 100 kilowatt threshold into the mini hydropower range. Now, as we start to move into that slightly larger range, you'll notice that the construction, the footprint of these that initial investment cost has gone up as we've crossed that threshold from simply install on a pipe to perhaps something that is going to require something more like a power here. It's a low head site. It appears where there may have been an existing lock that they modified to utilize that dam and that change in the 12.5 feet of head by installing this powerhouse with an output of 169 kilowatts. I will quickly mention impulse turbines as my last example of a closed conduit hydro. Impulse turbines work on the principle of free jet velocity. In other words, the flow through the penstock ends in a nozzle. This nozzle converts the potential energy into kinetic energy. The turbine runner, this piece here, is spinning in air. So the housing is this blue piece here, or this piece here, that contains the turbine runner, is not fully immersed in water. There's just water spraying from the nozzle and splashing around in there and then exiting that housing. And the impulse turbines, which can be a Pelton wheel or a turtle wheel, work best in conditions of high head, say in the range of 300 feet or greater. They grant the capability to produce some amount of power in a situation with very high head. Say, for instance, a small stream that cascades down several hundred feet of a steep hillside. This is a larger scale impulse turbine. Notice we've crossed the 1 megawatt threshold, and the significant amount of auxiliary equipment that becomes necessary to support units on this scale. Open channel installations are those where we are not taking advantage of any significant change in head. Instead, the requirement becomes the waterway with a significant flow rate, and preferably a channel profile that allows for installation of the open channel or hydrokinetic installation reasonably close to shore. Canals often fit these requirements well, and be aware that hydrokinetic technology is in its infancy, and many installations have only been for trial purposes. As hydrokinetic turbines don't require a pressurized water passage, when they are placed in a river or canal, they can be placed in series with just enough spacing to allow the water to gain a steady flow profile, perhaps as little as a few hundred feet spacing between the units. As the hydrokinetic turbine is rather large and requires a certain velocity for the flow, we are presented with minimum parameters for the flow rate and profile of the waterway. This is an example of an open channel or hydrokinetic turbine on the Rosa Canal in Washington State. This is a burial reclamation project. As you can see, the canal has a consistent, narrow and deep profile and a significant flow rate. This unit, manufactured by a company called InStream, is supported on a large pipe that crosses the canal. The unit has the ability to rotate 90 degrees out of the water. So in the bottom picture, we can see that the turbine runs the energy with the flow of the canal. Well, the top picture here shows it rotates degrees up, and we can see that hydrokinetic style turbine looks like maybe something we use in a blender or something, blender blades. Now I'd like to revisit the fluid power equation. Again, recall their factors are head and flow. The proportionality constant, the C that I mentioned here, is determined by the conversion factors, depending on the units that we use for head and flow, as well as the specific weight of water, such that the head is actually converted to pressure. As this expression is the ideal power available in the fluid flow, then to get an actual approximation of the power output you could actually achieve with any hydro unit, we would need to apply an efficiency rate to this ideal. For microhydro range units, we might assume 80%. And for, say, the cross flow unit that I introduced a moment ago, that 80% is a reasonable number. All Also, if the flow you are considering is a stream, be aware of how much that stream's flow you might actually be able to utilize by rerouting through a penstock and microhydro turbine. I will introduce some applicable equations on the next couple slides, but to give you an example of scale, we might achieve 100 kilowatts with 20 feet of head at 74 cubic feet per second, or we might scale back the required flow and still achieve 100 kilowatts if our head is then increased to 100 feet and the flow was reduced to 15 CFS. Now, with these equations that I present on the next slide, I use the same notation that I used in the tech note, where uppercase P is power in kilowatts, uppercase H is head in feet, lowercase p is pressure in PSI, uppercase Q is flow rate in cubic feet per second, and lowercase q is flow rate in gallons per minute. So here are those equations with the factor of C applied. So just be sure if you are to employ them when you're looking at a stream or a pipe, you are paying attention to the units you're using. And keep in mind that these are just an ideal. Don't forget to apply your 80% assumption for efficiency. I present these equations here and in the tech notes as what we might call a screening factor. So let's say you have a small dam or a cascading stream on some property that you would like to assess for its microhydro potential. You can make a determination of the change in elevation for a conduit and make an assessment of the flow rate, and then apply one of these equations to give you an idea of an approximation of the range of power that you might possibly achieve at the site. Additionally, if you know your flow rate and you are considering the size of a pipe that you might need to add or the size of an existing pipe that you may want to utilize, note that most turbines have a limit to the velocity of flow through the penstock. Additionally, slowing the velocity of the flow will reduce the friction losses through the penstock. So as flow rate is the product of velocity and cross-sectional area, you can make an approximation of your necessary pipe size by dividing the flow rate, if you're using cubic feet per second, by just 7.5 feet per second to give you the cross-sectional area of your penstock. An approximation of the whereas with the previous slide, where I was discussing the ideal fluid power equation, going through that to provide a quantitative screening method for site evaluation. Now I can go through some qualitative attributes of what makes a good site for microhydro development. Those good attributes start with high head. In other words, a tall dam with an existing pressurized outlet and sufficient excess flow that might be routed through that existing pressurized outlet. Minimal disruption on a flowing stream or river. By this, I mean if the site you are evaluating does not already have a dam or other infrastructure in the water, then the viability of that site for the addition of microhydro will be dependent on adding new water diversion infrastructure to the waterway. So the less invasive you need to be when making construction changes to your waterway, the better, as it increases, your environmental hurdles and your construction costs are going to increase as well. As just mentioned, existing infrastructure, such as a dam, is a beneficial attribute. On that note, your next assessment might need to be, does this dam have an existing auxiliary pressurized outlet that can be utilized, or perhaps some other means of delivering pressurized flow from the upstream pool through the dam? It is also beneficial to be able to site the microhydro close to its grid connection for the point where you apply the load. If you identify a site that has good potential based on the flow and head of the stream, and yet that site is several miles away from its load, then obviously the project might become skewed by the cost of routing transmission lines and the cost of step-up and step-down transformers to go along with that transmission. are a beneficial factor for a number of reasons. Primarily, we want to keep constant flows for the sake of being able to easily size the turbine. Additionally, constant flows allow us to avoid control mechanisms that would be necessary to switch the unit on or off, depending on the unit's ability to handle the flow that it's seeing. An irrigation canal, or similarly a river with a narrow, deep channel and high flow rates, would be feasible for the purpose of a hydrokinetic installation. Now, attributes of a difficult site. Some of these are merely the opposite of those positive attributes that I just listed. Impounding a free-flowing stream would likely require a more rigorous environmental and regulatory review, as well as more substantial construction costs. And diverting a substantial amount of water from a free-flowing stream would also entail environmental and regulatory concerns. If there are migratory fish or endangered species in that stream you are considering, then the hurdle to diverting or impounding that free-flowing stream would become even more daunting. So, let's suppose that you have screened a possible microhydro site and it suits some of those positive attributes that I just listed. So you now want to proceed to a more in-depth study of feasibility and project implementation. This is the point at which you would most likely involve HDC, but also include a variety of other professionals from the applicable USACE district or division office. Personnel involved in regulatory, environmental, legal, hydrology, contracting, cost estimating fields, and others as determined. This team could be led by a district-level project manager, as that's what the largest hydro that we deal with. As the feasibility investigation proceeds, it would be beneficial to have multiple points of go, no-go decisions defined. These would typically be economic decision factors, but would also need to be defined based on the unique characteristics of the site under consideration. I would now like to discuss briefly the additional considerations you will need to assess once you are proceeding with a microhydropower feasibility study with a district team in place and HDC involved. The type of generator you select influences the type of switchgear and controls that are necessary for the unit. Simultaneously, this consideration goes hand in hand with the nature of the load to which you are applying the power, the electrical power produced. The simplest arrangement would be an induction generator supplying a battery bank. Other possibilities may include generation connected to the distribution grid, or a setup with a control system that allows for the microhydro generator to contribute to the grid, but serve as an independent power source when the grid is down. In all cases, the cost is dependent on how detailed and complex the system becomes. One more important factor to keep in mind where generation is concerned is that USACE is prohibited from adding commercial generation capacity to sites that do not already feature that capability. In this regard, microhydro installations should be sized to suit the load demands of the USACE facility where it's located. However, if this generation is tied to the grid, there may be some legal complexity prohibition in regards to the average power produced versus the average power consumed, particularly in light of likely large fluctuations of those facilities' demand for power. Controls can be kept simple, or it can be as complex as desired for the purpose of, say, economy of the microhydro unit's operation. Controls can address the mechanical operation, or breakers and switchgear, or perhaps the diagnostics for the unit's operation. As we saw with the earlier example, the scope of necessary control will definitely increase with the size of the unit, but will also be a function of how autonomous you want the unit to be. The cost of controls may be largely reflective of the unit output, but also be subject to variation of a site's unique conditions, such as fluctuating flow rate or variability in the situations where the generator can be connected to the load. The bullet at the bottom of the slide addresses the demand side of the generation and load relationship. With large-scale hydropower, the generation is synchronized with the grid. The power output of the powerhouses is determined by the load demands of the grid, but that output is controlled by turning the hydro unit on or off and then setting the hydro unit to run at a given output within the operating range, which in turn is controlled by a governor that throttles the flow of the turbine. With microhydropower, it might be more beneficial to allow the turbine generator unit to run simply at its design output and add controls that change where the electrical output load is applied, connected to the grid or to a battery bank, or interchangeably based on the on-site electrical power demand of the facility where you're setting this microhydro unit up. Variability. As more manufacturers have emerged, producing turbine generators and control system packages in the microhydro range, the equipment costs have stabilized to predictable ranges, but the variability is introduced by the extent of modifications that would need to be made to a site in terms of the civil construction, building the powerhouse, or adding a small dam, laying down a penstock, or building transmission lines, to name a few considerations. With large powerhouses, you can find cost projection curves that relate the size of the facility in terms of megawatt output to the expected cost of constructing that new facility, but this predictability does not really extend to the microhydro scale, as unique situations may drive construction costs by full orders of magnitude. These costs I have listed here are for rough estimates of equipment only. Those variable civil construction costs are not included. Also not included are engineering costs. And now, I would note that USACE is traditionally an organization that prefers to design robust installations with long design lives. Where microhydro is concerned, perhaps we might need to accept a higher degree of risk in terms of allowing the project to not be successful or have as long as the design life as we would apply in other situations. Recall from the earlier slides on specific equipment that there's a microhydro scale unit called a Toshiba E-Kit. Toshiba provided us a quote on equipment, a turbine and generator unit, for a 35 megawatt unit at $165,000, with a control package included. This 35 kilowatt, 35 kilowatt. Operation and maintenance also need to be an important part of the go-no-go factor in the assessment of a site for microhydro viability. Regardless of the level of control and autonomous operation, there will be a routine maintenance and more major maintenance that may need to be addressed by the staff of the facility who are surveying for microhydro. Cost considerations could be made weighing the costs of operation and maintenance against the benefits of having self-sustaining on-site efficient capabilities. This would require a comparison of the cost of the operation and maintenance versus the cost of the initial control. Here I'd like to cover some of the non-technical hurdles to implementing the development of a microhydropower installation. I previously mentioned the prohibition against turning a non-powered core dam into a net power producer. Additional considerations might extend to whether or not adding microhydro impinges upon the authorized purposes of a facility. These are questions that would need to be posed to a district's legal or regulatory professional. Similarly, the environmental and endangered species considerations are a good reason to be sure environmental engineers are involved early in the discussions of microhydro feasibility for a given site. Implementation schedule. When seeing a project through the feasibility study and bringing it to fruition, the full length will again be dependent on site characteristics. If the site is ready for installation of equipment, let's say for instance there is already a pipe in place with a pressure reducing valve, and all we need to do is replace that valve with a off-the-shelf microhydro turbo unit, and the process might be as short as 6 months. The site requires more extensive development, including civil site work in the rerouting of a waterway. The process will be including the examples of the Toshiba Hydro E-Kid turbines or the Osberger crossflow turbines, among others. Off-the-shelf prepackaged equipment, including the turbine, generator, and control system, is available in the Microhydro range. Once we cross the threshold in the mini hydro range, or once we cross that threshold of about 100 kilowatts, more engineering and investment becomes necessary, as the units must be largely customized to their application. The benefit equation, we must identify what drivers make a project worthwhile if the economics aren't the primary consideration. It is important to define what level of economic payback through energy savings justifies the investment, but we might also define some level of value for what we might term the ancillary benefits. In some cases, that may be driven by policy, such as net zero goals or energy security. In many cases, existing dams that do not already have hydropower have been reviewed extensively for their potential. The Corps has flood control dams in the North Atlantic Division and navigation dams in the Mississippi Valley Division or the Langston Rivers Division, where private entities have filed for FERC licenses and have been granted the right to develop private hydropower at these Corps properties. For those that have or are in development or have pending FERC license applications, they may give us some insight into a site's viability for hydropower development. But keep in mind that these are driven by the economics of those FERC licensees establishing viable commercial power production. If the goal is on-site use of the electrical power, then not only is it possible for the Corps to pursue microhydropower from a legal standpoint, recall again that the Corps can't add commercial power production to a non-powered dam, but it is also feasible from a perspective that those FERC licensees might not be considering. I would even recommend that withdrawn FERC applications can be a kind of a research starting point for looking into a site's potential. Perhaps there are details there that, while it indicated that the site wasn't viable for a larger development, it may be fruitful for a smaller installation for this on-site power usage, generation of on-site power. A case in point is John Redmond Dam. This is a USAID flood control and water supply dam in Kansas. The Corps commissioned a firm to look into the feasibility of hydro development at this site. What makes it particularly appealing is the existence of 3 auxiliary pressurized pipes that pass through the dam. But that study focused on maximizing the potential of John Redmond Dam, which would ultimately have rendered it a net power producer in excess of 100 kilowatts. Additionally, the cost of development were projected to be substantial, in part based on the scale of the proposed development. If this were reevaluated from an energy independence perspective, perhaps sizing the turbine, then this is a good example of a site that does have microhydro potential. Another case study included in the tech note was a feasibility study performed for the Air Force Academy. A variety of water sources and pipelines were included in this study on the Academy property, but ultimately none really panned out for reasons including water usage agreements or technical reasons that were identified once a little more scrutiny was put on them. It's certainly not my intent to be discouraging, but there are a variety of factors that may be some limiting once you look more closely into what initially seems to be a promising site. Similarly, this is another site that did not quite pan out, but under slightly different circumstances, it could have been a very viable microhydro site. Now, this is a Minnesota National Guard facility that has contaminated groundwater that is required to treat. So it pumps that groundwater to a treatment facility, and then it's pumped again from that treatment facility across the distance to a point where it's discharged into a pond. The final run of that effluent through that outlet pipe is gravity fed, so it pumps it to the at the top of the hill, and then from that point it's gravity fed. So there was interest there, intrigue, regarding the possibility of using that final stretch of gravity fed pipe to install microhydro on the order of about 25 kilowatts. Ultimately, it was found that the pipes would need upgrading, and the transmission distance and other technical factors unique to the site made it too costly, or at least costlier relative to other means of sustainable electrical power production, such as solar. The Corps was involved to some extent, in not CC, but the Corps was involved in introducing microhydropower capability to rural villages in Afghanistan. These instances provide a good example of what microhydro can be, particularly of serving an isolated grid. That's what made this pursuit truly a viable option for providing power to these remote villages. And note that that turbine in the picture there is a crossflow turbine. As I mentioned before, it's very useful across a variety of smaller output ranges for turbines, and designed for easy operation and maintenance. Also, in comparing what we might pursue for a remote site in Afghanistan, can be subject to some differences in how we would approach it here based on water usage laws and environmental concerns. And in the Afghanistan case, may have made it easier for those projects to move forward, but note how useful a simple small microhydro installation can be, particularly for a remote site where the establishment of other energy resources can be difficult or costly. In summary, there are a wide variety of turbine types available, and microhydro can be a viable means of introducing sustainable on-site generation to make a project energy independent. But that pursuit must start with well-defined goals and a careful analysis of the potential roadblocks. I hope to see a microhydro project, so I hope it imparted a good understanding of the necessary evaluation criteria and the basics of hydropower to enable you to bring some promising sites to our attention. Thank you for taking the time to listen to my presentation, and I would now like to have Eric assist in fielding any questions you might have.
Yes, folks. Thank you very much, Mr. McAllister. And basically, people, if you look to the bottom right-hand corner of your screen, you will see a box, a text box with a gray send button next to it. Please type your questions in there and hit send. They will appear on the screen, and I will read them aloud for the sake of the recording, and also to manage any redundancy or flow of information, that kind of thing, and keep you from talking over each other on the phone. So anyway, so start entering your questions. I see Randy Shedd says thank you. But one thing you mentioned that there was a prohibition on the Corps adding power to non-powered facilities, like a levee or a dam that wasn't already powered. Can you give us a little more detail on what form that prohibition is, and was that only talking about commercially available power, or would something that's off-grid be prohibited as well?
So if it's off-grid, it's just providing power to the site, it's allowable. So the prohibition, I believe, applies to what would be made commercially available, so tied into the grid, and in addition to being tied into the grid, providing a net amount of power to the grid versus just offsetting whatever.
So basically, if we were competing with the private sector utilities.
Correct.
Okay. So there's a question from, let's see, this question, has a microhydro feasibility study been done on any income installations?
Sorry, I'm not
Sorry, I know you're a researcher. Installation Management Command, that's the people that run the Army facilities, basically Army forts and installations, Fort Gordon, Joint Base Williams and McCord or something like that. Military facilities.
So, yes, there have been some. So that example for the Minnesota Army National Guard, and also there was one study done at West Point as well.
Okay. Yeah, I don't think those are MCOM, but I don't know if West Point is in. Maybe I should know, but I don't.
This is Charlie Allen. I'm sitting in here with Jack.
Mm-hmm.
About 5 years ago, we did a survey for all of the Army sites, and came up with, I think, about 3 of them that had potentials of approximately 1 megawatt of output. And those recommendations, or those, after finding those sites and writing a report of the feasibility, if you will, nothing further developed from that study.
Okay. Yeah, I think the DOE also did a large study of civil works in general in America, most of which were owned by the Corps, and reported a great deal of capacity. But like you were discussed, there's a lot of different legal issues and things that limit that. Now, I believe, if I'm not mistaken, that not sure if it's the right term to use, the IDIQ contract, but the Huntsville Center has a large contract that was set up under Ms. Hammock for renewable energy generation by a number of different ways, and I think hydro was one of them, where they could access commercial providers to do private-public partnerships to install various plants. That might be a vehicle to look into, because the funding is always an issue. Lori Arakawa from POD asks, are there considerations that need to be addressed regarding power quality when connecting to a building or other equipment to the hydropower?
Okay, this is Charlie Allen again. By power quality, I'm assuming... Okay, let me say some words here and see if that answers the question. Generally speaking, when we're talking about hydro on the scale here, once you get into, shall we say, a 10 kilowatt or larger, we have really 2 choices. We can either do a synchronous generator or an induction generator. Induction will have some issues with the quality, if you will, but they're not that big. Synchronous will be more expensive, shall we say, slightly cleaner, but for the purposes of these installations, unless you're running isolated, generally speaking, an induction generator will work. I think from the context of the person asking the question, it was perhaps founded in the possibility of these being DC generators, something of that nature. And you're only going to get down in hydro, in DC production, if you're down sub 5 kilowatt range. And usually that's not something that we would be dealing with.
Okay. Oh, and also, by the way, if people are looking in the bottom right-hand corner of their screen and they do not see a text box with a send button next to it, up at the top right-hand side of the screen, there should be a little balloon with the word chat under it in gray. You click that until it turns blue, and the chat window should appear if you don't have that already open. I believe it comes open by default, but maybe not on everyone's computer. Lori says that yes, that answered the question, by the way. So there is another question. Has the Corps of Engineers installed any Microhydro installations to replace the low flow valves on the outlets of our dams? That you know of.
Not that we're familiar with, no.
Okay. Let's see here. And the study that you mentioned about the 3 or 4 installations that might have had possibilities, Who received that? Was that the G4 INCOM or maybe Ms. Hammock's office, ASA, IENE? IENE?
I don't recall. We did that 5 years ago. I can certainly get that information.
Mm-hmm. Okay.
And forward it to whoever is asking the question.
Okay, I know that Ms. Hammock's, she was pursuing a lot of the net zero initiative at about that time frame. And I know that they had a lot of different information available on that. And some of that can be reached on I believe, the ASA IENE website. They have some links to where it says net zero power or net zero energy, and they have a lot of information on there. But basically, we are rounding up the hour, and yes, there's I'll send you a email address that somebody sent me to request a copy of that. So I'll send that to you. And with that, thank you, gentlemen, for your time, especially Mr. McAllister, for your time in giving us this technical information. Very informative and deep presentation. And again, we have the whole building design guide hosting our tech note number 28. There's a section of tech notes with a lot of other subjects, purple pipes and phase change materials, things like that. Feel free to check those out. This video will be posted on our Sustainability Mercy site along with a quiz, and people who have continuing education requirements, and if they are a registered AIA member also, they can fill out the quiz, send that to s_e-webinar at youthbase.army.mil, and with their AIA number, and we will get you, we will send your credit in for your CEUs or learning units, depending on which organization you're applying them to. So, thank you very much. I'll now stop the recording and wish everybody a very nice day.